Hello everyone. I'm going to go through a few slides to give you some details on how to do Lab 3 around precipitation analysis, taking real data to generate probabilities of precipitation, and how you might interpret them in the context of the lab questions that are posed on Canvas. So let's jump right in. So the first thing we want to spend a little time with is talking a bit about what are our learning outcomes. So we're going to do a few things today. Really, the idea is to give you some exposure to getting real data that is going to be used by for this lab, and it's a little, sometimes real data can be a little messy, can be a little difficult to find, and so I give you a pretty straightforward way to go get data for this particular part, but a lot of times getting data is one of the trickiest things that you do sometimes when you're working with these kinds of analyses. Once we get our data, we're going to play around with it in Excel, so we're going to spend some time doing some calculations, but also creating a spreadsheet that is really useful and organized and well noted so that you can use it later or others can understand what you've done. And then also being very good practice on how do we present this work so that others can interpret what we did. Remember, you have two resources, the technical memo as well as the guidance for visuals, figures, tables, etc. So when we're doing a frequency analysis, the thing that we want to be very aware of and thinking about, sorry, my floating screen is kind of in the way here. Let me see if I can move that real quick. Pointer off and then get this out of the way. There we go. Okay, so when we do frequency analysis, there's some criteria that we want to make sure that we're paying attention to. These sometimes just might be limitations because we can't always meet every criteria, but we want to do the best we can. But the first one is pretty important. And essentially what we're saying is that we want each event to be independent. And that is a statistical rule. When most statistics, we want those events to be independent of each other. If they aren't, we can correct for that through different kinds of statistical tools, but in this case, it's a little more challenging if they're not independent. So in the case of daily rainfall, which is what we're going to be using for this analysis, and we're actually getting daily max for each year and then doing the statistics on those daily maxes, we're pretty well hitting number one. The next one is a little bit more interesting, and it's thinking about how representative is our sample for what we're trying to use the data for. Are we trying to be representative of the past and potentially future conditions? Because often when we're doing return period estimation, we're trying to do a future design. So we're trying to create something, whether it be a green infrastructure practice like in a city, like a wet pond or something like that, or designing the size of an agricultural drainage ditch. We want these to be sized to be resilient for the future. And a couple of things come to mind when thinking about representativeness. So the first is that you want a really long period of record. So you capture enough variability throughout your climatological record so that you can actually understand what's the likelihood of an event happening. So you capture enough of that variability. Generally, we don't want to extrapolate a recurrence interval beyond our period of record. So if you're trying to estimate a 100-year event, you kind of want to have 100 years of data. Granted, that's a little tricky when we're thinking of like a 500-year event or something, and there's other tools to be able to help us get there. But yeah, so how representative is that data, and is it covering the period? Do we have enough of it to represent the variability is pretty important. One thing to think about is our early days of recording, we might actually have some numbers from, let's say, the 50s or even the 20s, right? And the kinds of methods that they use may not be as precise as what we collect today. So thinking a little bit about precision is important for older historical data. And then when we think about future conditions, we're in a period of climate change where we have increasing periods of wetness. We're predicted to continue to be wetter on average. However, that on average is challenging because we are seeing, and the records show us this too, and the models predict that we will see more periods of drought with bigger floods in different periods of time. So big spring floods and then maybe some more drier drought-like summer conditions. So that's kind of what we see often in Iowa in general, and it's kind of predict it to get even more intense. So is our period or past record, past climate really appropriate for the future? Maybe, maybe not, but just something to consider as you're thinking about what your design is going to look like. And last but not least, sometimes depending on what it is you're designing, it can be helpful to organize by water year, October 1 to September 30th rather than the calendar year. And that just does a better job of accounting for water storage in the soil over the winter and water use by plants through the growing season. When we're doing any data-driven analysis, essentially what we're doing, we've talked about this already quite a bit, is that frequency analysis that we're doing here, any of it is really fitting an equation to data. And what we're doing today is fitting a data distribution to some precipitation data, and then also kind of doing some algebra to try to linearize a model for that distribution to be able to predict some fit parameters so that we can use it to help us predict what a 50-year return period precipitation would be for a particular location, for example. So we can use lots of different equations to do so. Many of you have seen a log distribution. We can talk about the normal distribution as well. That's kind of just a regular linear line. That's not very typical for any precipitation data. Log distributed precipitation data is not unheard of, so we're going to try that one. And then we're also going to use this one that works really well called the Weibull distribution. And it's a little more complicated, not so much though. I'm confident everyone in this room can handle that. But it's really versatile. So because it's a little more complicated, it has a few more parameters in it, we can use those to fit varied distributions, including an exponential or even highly skewed distributions. So pretty useful tool, and I'll kind of walk you through how that works. So first I'm just going to spend not a lot of time, but kind of walk through the process for how you do this when we're using that log model, the log distribution. So I'm going to pause after this and go to Canvas and kind of walk you through a little bit of the assignment. But here's really briefly how we do the probability and return period analysis. So this is after you've got all your data organized by year max precipitation, ranking them in order from ascending smallest to largest, with the smallest being number 1. Then calculating these various parameters. So you make a bunch of columns after that. Got your data organized. So you've got, I'll show you this in an Excel spreadsheet in a minute, but you've got your data organized with year and then max precipitation in the next column. And then after that, you're going to calculate what we call the plotting position, which is simply lowercase p. I is the period of record that the one record that you're working with, that row, and is the total number of years, and just +1. So you calculate the plotting position. Then from there, you can calculate the exceedance probability, simply 1 minus that. And then you can calculate the recurrence interval, R equals 1 over Q, and then you can do some plotting to see what that looks like. Okay, so the log is pretty straightforward, not too complicated formulas or too much of that stuff. So let's do a little bit more about the Weibull, because I want to make sure that we're clear on this one. So slightly different for the Weibull distribution. Instead of ranking them in ascending order, we're now going to rank them with the largest on the top. So largest is going to be number 1. And then instead of just a relatively simple calculation for the plotting position, we're actually going to do it a little more complicated and follow this formula that's listed right here. Oops, sorry. And essentially that now has rank, that's the order, the one that you're using. So that in the previous case was I. A in this case is 0.4. I said the Weibull can be used for a lot of different distributions, and that value of A is how you can tweak it to follow these different distribution patterns. If you don't really know what it is, you can use 0.4, and that's pretty common. But if you do know, you can apply a more precise value of A and get a little bit better fit of your model. Grad students, I'm asking you to actually take a look at the distribution, make a histogram of that data, and undergrads, if you'd like a little bit of bonus points, you can do this as well. And essentially what you're going to do is take the distribution of all of your annual maxes, plot those, see what the fit looks like, and if one of these might be better. And you can do a little bit of research online too. These were just a few that were in your textbook. There's lots of other ones out there. Okay, so once you get all that plotting position sorted, you can do a plot that looks like this. Plotting that versus precipitation. So you're calculating P versus precipitation depth. And now, what we're really trying to do though is fit this Weibull distribution function, which is listed here. Cheapers. Sorry about that. And essentially, this probability distribution function, actually it's cumulative distribution, is an exponential, and it's got, here's our precipitation depth. There's lots of P's and probabilities and plottings, so apologize in advance if I use them incorrectly, but they're easy to get mixed up, so kind of paying attention to what they are is really helpful. And as another aside, this is really well described in your textbook as well, and it's in chapter 3.11. So there's several pages on how to walk through all these equations and how they get to where they are. I'm going to give you the short version here, but go please read that section of your textbook for a little bit more information in depth. So we can take this exponential version of this cumulative distribution function and linearize it using the properties of logarithms. So that is what's listed here on the bottom. So I'll turn my little pointer back on, and that's what's right here. Log, E, here's our natural logs, and all these things are kind of rearranged. And this might start to look a little bit familiar because it actually now follows our lovely little linear model, y equals mx plus b. And if you come over here, here's our y. You can calculate all of that. We just do a bunch of logs of that cumulative distribution value, and we already calculated that. We've got beta, which we're going to fit. Now here's our x. We know that because that's our max precipitation. That's our x value. And then here in purple is our intercept. Well, intercept has both beta and alpha, which is kind of complicated. But if you plot this at first, you can get beta and then plug beta in to get alpha. So I'll kind of show you this in a spreadsheet format here in a minute. But what do we do with all that data, and why is this helpful, is we can start to do things like answer questions like, what is the return period for a certain type of rain event? So we can plot these in here. Here's our Weibull probability distribution function. We know 100 millimeter rain event. We've got our alpha and beta that we fit with that distribution that we just created, and we can actually return that number as a percentage of likelihood, and then also turn it into return period by just taking the inverse, getting the years that it would likely reoccur every 6 years on average, right? We always know that these things are statistical representations, can happen on average every 6 years, but that's the long game of on average, how that behaves over time. We can rearrange this guy and actually solve for x instead. So we might want to know what is actually the precipitation when we have a return period that we are designing for. This bottom part is a lot more common in design, where we're saying, hey, I want to design a channel to convey the 25-year storm event, for example. So we know what that is. That's what our design standard says. Well, we need to know what that precipitation might be. We might get that precipitation, and then we can turn that into a discharge that we might expect at a certain watershed size, etc., and move along from there. So generally when we're doing design of channels, we actually start with the discharge, but that was kind of the example that I had in my head at the time. So really trying to kind of think about how we might use these data in a helpful design context. Okay, I'm going to pause the recording, and I'm going to go over to Canvas and show you what is up next. Okay, so we're back. Here is your lab assignment for lab 3 and this precipitation frequency analysis assignment. I'm going to briefly walk through this because all this is, I think, really clear, so I don't want to spend too much time. But there's a little scenario devised for you about some issues related to erosion during a construction project, and essentially who is to blame for that. Did the contractor not do what he was supposed to do in taking care to prevent erosion from happening? Or was this the event of the century and he had nothing to do with, there's nothing he could do about it? So that is your task. Analyze the data to see who is at fault. All right, so using data that we are going to collect from this Mesonet website, you're going to go to this website, scroll a little ways down, find these daily observations, and you should be able to kind of walk through this bit of information here to do that. I'll kind of go over to Excel and show you how to use a pivot table to filter your data and how you might go about that. I've given you some hints here about how you might position your data. Like I said in the presentation, you're going to do two types of distribution fits here. First one using a log distribution and the second one using the Weibull. So I'll kind of walk through those for you in Excel briefly. I'll do the Weibull one. The log is pretty straightforward. But again, I put all the little bits of detail here that we just went through in the presentation right here for you to have handy. And then, like I mentioned, grad students and undergrads, if you'd like a little extra bonus points, investigate how that plotting position formula is really built and does that make sense for what you're doing. Do a little bit more data analysis to do that. And then some interpretation. So there's some questions I ask that you should be addressing in your memo. So everything is going to be uploaded to Gradescope a week from today. All right. I'm going to pause again. Okay, folks, so here is some data, not the data you're actually going to be using for your lab, but some other data. And I wanted to show you really quickly, if you're not familiar with pivot tables, how this works. So I pulled down some data from the Musenet from a different station, and I'm going to show you relatively quickly how to use this pretty awesome tool. So one thing that you'll notice is this has the station date, day. It also had day of the year and precipitation. I added this column called year, which is an important piece of information you need to have in order to be able to sum them by year or get a max by year or whatever. You kind of need that separated out. So that's an important little step that you don't want to forget. So to start with, I'm going to select all of my data, and I'm going to go, see how I can like move around with it. I can get that back up there. Okay, so now I've selected all of my data. If you're not familiar with that, there's a Control Shift arrow shortcuts that you can use to quickly select data in Excel, which is pretty handy little tool to figure out. I'm going to go over to Insert, and I'm going to insert a pivot table. Note that the data is highlighted, so it jumps it in right here. And I'm going to put this on my existing worksheet just to keep it easy so you can see the differences. But normally I would say put on a new sheet just so you don't accidentally overlap your data or run out of room for your pivot table. So we're going to put it right there for today. Note that this is on a Mac, so some things might be slightly different than how they look on a PC, but hopefully pretty similar. Okay, it looks like everything's sharing correctly. So once you do this, what you're going to start to see is this kind of blank pivot table section right here, and then this fields list and all of these different boxes over on your right hand side. Notice the field names are simply the column names from the data set that I selected. And so for this case, what we want is to go by year. So I'm going to come over here and I'm going to highlight year. I'm going to pick it up and just drag it into the rows. And that's going to show up right away in my pivot table. So now I'm going to see all those rows. If you accidentally put it in a different spot, like say, oh, I want it over here. Oh, well, that's going to put them over on the side. And then you're going to make this very wide table. Maybe you're saying I want to go here. You can also do things like I want to put a filter by station because maybe I have a lot of stations. In this case, we only have one. But you can imagine a case where you might have downloaded several data sets or you want to combine them or various ways. So you can use pivot tables to do some filtering too, which is kind of nice. So we only have one, so I'm just going to go ahead and take it out. And you can just remove things by just simply grabbing them. If you didn't catch that, I had that sitting here. And I'm like, no, I actually don't want that, so I'm going to come and grab it and I'm just going to slide it off and it goes away. So what we want is by year, we want to sum up or get the maximum value rather of precipitation. So when I bring that down, it says sum. I actually want to switch that. So I'm going to click on this I and make that a max. So now I can get the maximum value of precipitation in inches. Sorry, no label there, but these are the max daily precipitation values for each year of my period of record. So that's what you want to get to, and that's what we're going to use moving to the next step. Okay, so if I go to my next sheet, I actually did this on a shorter set of data. This is the full period or more full period record, that same location, 1968. In this case, I think down to 2018. Yeah. And so these are just organized by year. The max precipitation, I convert it to millimeters just for kicks because I'm going to do everything in SI units. And note that this just has a ranked position. I just left it 1 to however many every years I had, 50 years of data or so. The first thing, if you recall, we need to sort and organize this by precipitation total. And I'm going to organize this with the biggest precipitation on top. So I'm going to go over to data. I'm going to sort this by precipitation. Instead of smallest to largest, which is often the default, we're going to pick largest to smallest. Okay. And now we're going to have that be sorted properly. The next several steps, I've already got the formulas in here, but I'm going to just kind of walk through them. So in this case, here's that plotting position. No, I'm doing all of this for the Weibull distribution approach. So this is this equation up here. So you'll see M minus A. In this case, I've chosen to use 0.375 because for this particular location, I did do the distribution of data, and it is very normally distributed. So I felt comfortable using this value instead. For yours, you need to use 0.4 or do the distribution and have some justification for what you choose. Okay, so there's the A values are both right there. 51 is the number of observations, and then +1. So that's simply that formula. We're going to calculate that for all of our years of record. And then we're going to do a bit of a log version of this whole thing. So all of these guys are now ways in which I'm trying to organize that particular Weibull distribution function to get it linearized. So I am going to go back over here to this PowerPoint, which you can't see right now. I apologize. Let me switch. Can I switch? I guess I have to stop and try again. Okay, folks, I just went and grabbed this equation that was in our PowerPoint and pasted it in here. So we're going to show you how to put this into the linear form in your spreadsheet. So if you recall, this part on the left-hand side, that is our y, so that is listed right here. And if you kind of blow up that Excel formula, you see that that's ln log sub e is the same thing as natural log of this other natural log of 1 over b. And so that's what's posted right here in this little cell. Okay, hit return. And the same thing here, ln of the precipitation, ln of x, which is there's our x precipitation. That is this little component over here, the x value. So I'm going to copy those down for all of my years of rainfall. And you'll note that my Weibull distribution is now starting to get some information in it because I had it do some calculations further on down here. So what we're trying to do now is actually plot this y versus x, and I think I have that down here, hopefully. Nope, that is something else. We'll just plot it. So we're gonna plot, not super fast with my plotting these days, but bear with me. Find a little scatter plot. And of course it tries to be very smart. Ugh, gross. Let's not do that. Come over here, maybe it'll be less smart. Okay, now it's blank. All right, so we're gonna select our data, and I'm gonna select a new series, and we're gonna make the x's what we had here. Oops. And then my y values, these guys right here. Okay. And hit OK. And if you scroll up, and I do not know why that didn't show up. That was very weird. maybe I actually need to label a series first. Okay, let's try that again. X. I have some little values down there to round out a distribution to make it look pretty at the bottom, if that's what you're kind of seeing me not include. Let's try that again. There we go. So you can do this in a couple different ways to try to get these variables, but basically what we're trying to do is get beta and then this. And so I really like to use Excel's built-in formulas to actually get slope and intercept. So I would encourage you to do that. You can also use just the fit trend line idea, but that gets you a little bit tricky because you have to like read the numbers off and it's a little bit harder. So I would use those functions in Excel to return both the slope and intercept of your line. And then once you get those, you can put them somewhere here in your Excel sheet, and then you can calculate this value here, which is coming into here, this y-ball distribution. So you're actually calculating E, xp, there's the E, to the minus x, which is this precipitation value. And then these were the ones that I had done, but I hid them behind closed doors. So that is the fit of those alpha and beta values. And you can calculate that, and that builds like your whole y-ball distribution. Those don't mean anything to you because they're not really showing up at the moment, but the idea is you should get something that goes from a very small number all the way up to a much, much closer to one number. This now looks like it kind of should. So one thing you should start to see at the end is if you plot your probability. I'll just kind of click on this data so you can see what I plotted here. This is your probability plotting position, probability versus precipitation. So that's the data. And then this orange line, that is the model fit. Now I alluded to the fact that I was trying to like figure out a few places where that curve could get a little bit better resolution. I didn't have good data up here at the top, so I added in some and I just applied the model directly because it's simply a function of those alpha, beta, and then your precipitation. So you can put any number in there you want to. You could say, okay, well, I actually want that to be, I don't like this down here, I want a little more data down there as well, so maybe I'll put in, instead of doing, I'll just do another one, let's say maybe, how about 110, and calculate this, and then I'll say, okay. Oh wait, I think that's actually not going to work because it's not in order. What happened? Nope, it did. Okay, so now I can just go like this, and it's gonna screw it up. I knew it because they're not in order, so it's kind of trying to go up and down. All right, that'll teach me to try to do something on the fly. But those numbers are right. You can see it's actually there. I just need to resort it so it's in the right location. I'd have to put that one on the very top if I wanted to fill in a gap at the top. Yeah, that's all right though. You get the idea, I hope. I was just wanting to show you then what you're trying to get to at the end is something that looks a little bit like this, where you have your data and your probability model on top of that. And then from there, you can start to use these tools to answer some of the questions around the probability of different events being exceeded and whether or not that contractor is responsible for what happened. I'm also asking you to go to a website online that has all of these built out from the National Weather Service and compare what you were able to calculate to what they were and see how those numbers line up or not. So any questions, come hunt me down, send me an email, let me know how things are going. And I hope you guys have a good Tuesday, and I will see you all on Wednesday.